we're going to get started on the second lesson. So again, it's applications of specifically looking at exponential growth and decay. And so on this particular set of notes, we're just going to set it up. We're just going to look at the setup, the model, the equation, and kind of talk about the meaning and how to solve it in general cases. And in the next set of notes, we'll go to actual applications. All right, applications of exponential growth. So notes part 2. So this should be hopefully a review for most of you. Again, exponential growth and decay models, these would be the uninhibited exponential growth and decay. So somewhere in your algebra, chemistry, biology, they should have talked about these types of applications. Alright, so these are whenever something, a population, a quantity, grows or declines at a rate proportional to its size. Now, just to give you an idea of some examples of that, I'm looking at 2 different cases here. So the first case is the growth case, right? A population doubles every hour, right? So this would be growth. All right, and it's growing at a rate proportional to its size because it's the population's doubling by the population size every hour. So suppose I start out with a small population. All right, so I have 10 people. All right. After the first hour, all right, those would be hour 1. Those 10 people double, so it's growing by 100% each hour. So now I've got 20 people. All right, now the second hour. All right, again, it's growing by 100% of the previous hour, and so it's the 20 that gets doubled. Now I've got 40 people. All right, the third hour, that would double to 80. All right, the next hour, that would double to 160. And it would continue on in the same pattern. And so that's what we mean by growing at a rate proportional to size. It's growing by 100% of whatever its size was every hour. All right, every hour it's growing at that rate. Declining works the same way. And so my second example is a decay case. Suppose I have a quantity, right, and it's cut in half every 1,000 days. And so that would be a half-life. And then we use that term because, again, that's oftentimes used in science. All right, when things decline by half-life, all right? You have radioactive material, they decline, they have half-lives. All right, all radioactive material tends to have a half-life. And so that means it's cut in half in this particular example, it's cut in half every 1,000 days. So we start off, suppose we have 100 milligrams of whatever this particular material is, and after the first 1,000 days, so this would be my 1,000 days, it's cut to 50 milligrams. All right, then my second 1,000 days, so after 2,000 days, well, that's cut in half to 25 milligrams. All right, the next 1,000, which would represent 3,000 days, well, we'd have 25. The next 1,000 days, we'd have it again. All right, and each time we would divide by a half. And so eventually these fractions get smaller and smaller and smaller as time goes on. Now, they never reach 0. But they get so small we would consider them 0. All right, fractions just decrease. Again, we cut in half every 1,000 days. And that's an example of exponential decay. All right, when it's decreasing. And so in this case, it would be decreasing by 50% every 1,000 days. That's the percent at which it decreases. Every 1,000 days, it loses 50% of the previous amount. All right, the equation that we're going to use, and the equation that you need to know, is the following. All right, so the equation for exponential growth and decay, it's the same equation, and eventually we are going to get to continuously compounded interest, which again will be in terms of finance, but it's the same equation. All right, so this Q of t, which represents the Q of t is any quantity after time t, Q naught e raised to the k times time. All right, so again, same equation whether it's growth or decay. So now the parts. So Q naught is the initial amount. That's the amount at time 0, the amount I start with. All right, that's what initial means. So if it was my population, that was 10, right? In the previous example, we started with 10 people. Or my quantity, I started with 100 milligrams, all right? That's what I start with. And then it's either going to grow exponentially or decline exponentially. And so on the graph, that would be the y-intercept, the point where we start, 0 and our initial amount. All right, then t is always time. Time is the, when is it growing, over what period? So it's growing, hourly, over days, and again, that would be our time period. And it should be consistent. It increases by 50% every day, right? Or it decreases by 2% every hour, right? So again, it's the percent at which it grows or declines over a given time period. Alright, K. Alright, K is the one that in some applications will be given, and in some applications we will have to find K. K is what's called the growth constant, and it depends on how the population's growing. It's in terms of the relative percent growth or decay rate of an object over the time period. So that would be the I'm growing at 100% per hour, or I'm declining by 20% per day. Alright, so that's the percent at which, that's the proportion, the percent at which it is growing or declining over a time period. Alright, so the graphs of these. Alright, so what makes it growth or decay is that K constant. Either that percent is moving up, so it's positive, it's growth, or that percent is negative and it's moving down. So same equation, when we go to graph these, it's the same equation, but what changes is the K. So if the K is positive, I'm increasing. It's a growth, and the graph is the following. Alright, so we have our, okay, well we only graph in the first quadrant because it's time, right? This is time. And this would be quantity, right? Number of items. And so it's always positive. So only graph in the first quadrant. Domain would be all real numbers that are positive, right? Domain 0 to infinity, right? Time is positive. Quantity is also 0 to infinity. And you mark off your starting point, all right? At time 0, our population started at whatever that Q naught is, whatever that number in front of my equation is, right? That's my y-intercept. And then if it's growth, it'll follow an exponential growth. So again, it'll be a moving up, and there's my quantity at any time. The bigger the K, the steeper the growth. So if K is a large number like 50%, that's a fairly steep curve. If it's a small number like 0.5%, that would be a very small, now it's still curve up, but it's a smaller percent. And that's just, again, when we go to graph these, that's about as much detail as you need to go when we go to applications and we actually graph them. You just need to label your axes with your time and your quantity, starting point, and then the shape. Alright, decay, again, decay is the same equation. The difference is the percent will be negative. I'm losing 2%. So it'll be a negative amount. Also, only graph it over the first quadrant, right? It's still time. Time is still positive. It's still quantity. Quantities will be positive. They're never negative, right? Exponentials are never negative. And so we start off at 0, so 0 to infinity. And so we'll mark off higher, though, because our initial amounts are big amounts. So this is what we start with, right? That would be the amount of material we start with. And then it's going to decline. And there should be a curve to it. And it approaches the axes, right? Because my exponential function never is 0. So it never crosses the x-axis. Although eventually the fractions get so small that it zeroes out. Alright, so sorry about my phone dinged. Alright, so that would be decay. So this is growth, this is decay. And again, those would be the simple models. You'd have to label the time, whatever your quantity is. Same thing here. The bigger the percent, the steeper it is, the faster it gets down to approaching 0. The smaller the K, the slower it approaches that 0. Alright, again, we'll graph some of those in applications. That'll be a future lesson. Alright, so the last thing we're going to talk about in this set of notes is there will be applications where you'll have to find your growth constant, or there'll be applications where you have to find time. Alright? And so I'm going to go over the general case for that. Alright, the general case for solving for K or time. So again, the uninhibited growth and decay equation is our quantity at time t equals our initial starting amount, e raised to our K times time. Right? And K is either positive if it's growing, negative if it's decay. Alright, so to solve for either K or T there in my exponent, it's the same thing. Again, we've done these. We isolate the e term, so the very first thing we'll do is we'll divide by our initial amount. Alright, so we get our quantity at time t divided by our initial amount equals our exponential raised to our growth constant or decay constant times time. Right, the next step is to take the natural log. And it's the natural log of that fraction. Remember, don't round that fraction. If it's an ugly fraction, leave it. If it simplifies nicely, you can simplify it, but don't reduce, if you reduce it, it's fine, but don't write a decimal approximation, alright? Otherwise, you'll be significantly off. So leave that fraction exact. Alright, take the natural log of the other side. So again, inverses, so they undo one another. So I still have the natural log of that quantity at times t over my initial amount equals my growth or decay constant times time. Now it's whatever you're solving for. So this is, again, sort of where we get. And so if we want to solve for the growth constant, solve for k. Alright, well, k is just going to be that log of my quantity at times t over my initial amount, and that's inside my logarithm, and then we take that whole thing and divide it by my time. Alright, and the time would be given to me. Alright, so that would solve for k. If we want to solve for time, alright, same setup every time. Time is going to equal that logarithm of my quantity at time t over my initial amount all over my k value. Alright, so again, it would be whatever quantity we're looking for divided by my initial amount, and that goes inside my log, and then that whole log expression gets divided by my k. Alright, and that's how you solve for k and t. That would be the general case. Alright, now I'm going to look at two common types, the common types that typically show up in our application. And again, somewhere you should have seen these. You should have talked about doubling times and half-lives. Alright, so doubling time would be growth. Alright, so I'm going to start with doubling time. This would be if we're growing. Alright, so doubling time means I'm going to double, whatever my doubling time is. So I'm just going to write a generic double time. I'm going to write that a little better. Alright, so again, we're growing. Alright, double time. And I'm going to label my double time, again, it would be a number you would either solve for or be given. I'm just going to label it capital D. So capital D would be doubling every 5 hours. Alright, so it would be 5. Alright, so what that means is I should have twice what I started with at my doubling time. Alright, so when I plug my doubling time in, I should get twice what I started with. Alright, so we set the 2 times my initial amount equal to my equation with my doubling time plugged in, which is q naught e raised to the k times doubling time. Solve. So divide by my initial amount. And so what simplifies here is initial amount divided by initial amount's 1. And so I'm just left with 2 on this side, and e to the k times my doubling time on that side. Alright, now we take the natural log. So I get the natural log of 2 equals k times my doubling time. And so now it's whichever one I'm solving for. So if I want to find k, alright, so if the problem gave me a double time and I want to solve for k, I take my doubling time and divide it. Alright, I'm going to take k, I'm going to solve for k, so I'm going to take my natural log of 2 and divide by my given doubling time. Alright, and that's my growth constant. Alright, or if we're given a growth constant and we want to find the doubling time, and some applications will ask for that because it's an important, we understand doubling time, and a lot of times it's what we want to solve for. Alright, so we do the exact same thing. I solve for my doubling time by taking my natural log of 2 divided by my growth constant. And often in an algebra class or a science class, they'll tell you you can just remember these equations because they're ones we'll be using in application. And so it's up to you. You can either memorize these or you can solve for them like we did in the general case. Again, it should solve the same way we did here. So it's just up to you. If you want to memorize it or if you've already memorized it because you've seen them before, that's fine. Alright, so now I'm going to do the same thing for half-life. So I'm going to go over here. Same idea for the half-life. Alright, so an application would either ask for or provide the half-life. And so I'm going to label a half-life as a capital H. So a capital H would represent, after an hour, we lost half of what we started with. And so that means we take 1/2 times my initial amount is equal to my quantity when I plug in my half-life. Alright, so 1/2 times what I started with equals my equation with my half-life in it. So initial amount e raised to k times my half-life. Alright, and now I solve. So first step is divide out the initial amount, which again, those reduce to 1. So on this side I'm left with 2. On that side I'm left with e raised to the k times h, which would be my decay constant. Now we take the natural log of both sides, and so I get the natural log of 1/2 equals k times my half-life. Alright, and now it's, well, which one do I want to solve for? Alright, so if the application gave me the half-life, and I need to use it to find my constant. Well, in order to find my decay constant, we take the natural log of 1/2 divided by my half-life. Right? If we want to find half-life, find h, well, we do what we did before with the doubling time. I would take my half-life and solve for it, and so it would be the natural log of 1/2 divided by my decay constant. Alright, so again, just depends on what they're asking for. Same thing, if you want to just memorize these, or if you've again taken a science class recently, or you remember this from algebra, you can just memorize these, as it's always 1/2. You don't have to. Alright, like I said, you could do the general case and look at that. And so I'm going to do one simple example just to kind of walk you through, and that's where we'll finish today's notes. We'll start applications in the next set. So I'm going to erase this. So give me a second while I erase this so I can do sort of a simple example. Alright, maybe I'll just erase up here. Alright, so we'll do a half-life example. Alright, so erased, good enough. Alright, so an example. Suppose we, again, I'm just going to use a generic quantity. All right, quantity is what we start with. So we start with, suppose, 100 milligrams. All right, we know in 5 hours, we only have 5 hours, it decays to 50 milligrams. All right, so that means the half-life is 5 hours. All right, find K. Find our growth constant. So there's two ways you can do it. You can either remember K equals the natural log of 1/2, because it's a half-life, over my 5 hours, over my time. And then you'd plug that into your calculator and go. But if you forget that, you can always revert back to what we did before. I know when I plug 5 into my equation, I should have half of what I started with. All right, I should have 50 milligrams. And so plug 50 in, set it equal to our equation 100 e raised to the k times 5, right? 5 is going to get me in 5 hours, I'm going to be down to 50. And then when we solve that, well, we divide by 100, and that reduces down to a half, and it always will if they're giving you a half-life. E raised to the k times 5, and then we take the natural log. That's where the natural log of 1/2 comes from. So we'd have the natural log of 1/2 equals k times 5, and then we divide by 5. And then we get that expression. So if you don't memorize it, it's okay. You can always set up an equation and solve it that way. All right? It's up to you. You want to memorize those equations, or you're going to remember the process, because this will work for any case. I don't necessarily have to have a half-life. I could say in 6 hours it declines down to a quarter of what we started with. All right, that would mean if a quarter would be 1/4. All right, so it'd be the natural log of 1/4 divided by 6 would give me out my k, right? If we have, in 6 hours we decay to 0.25 or 25% of what we started with. Alright, so if we wanted to find k, it would be the natural log of the quarter, the 0.25, or 1/4, divided by 6, and that would give me out my decay constant. So it works for all cases, just half-lives and doubling times are the more common cases, but it would work for any percent growth or any percent decay. Tripling time would work the same way. If I know it triples, I could do the same thing. It'd be the natural log of 3 divided by the tripling time. Right? How our quadruples, again, would work the same way. It'd be the natural log of 4 and the tripling time. Alright, so that's the setup, and that's what we're gonna get into on the next one. We're gonna start applications of exponential growth and decay is what we're gonna get to, but that will be the next set of notes, and so we are gonna stop this lesson there.